So we've got a panel discussion for the next hour on the sensor ecosystem. Unlike this morning where we wanted to talk about where sensors are in the world, I think in this one we want to talk about what are the technology drivers for sensors and what's happening in actually the building of sensors. And big question, is there synergy or is it a fragmented space? Yes, and the panelists, you've heard Paul talk today, we've heard Drew talk, we've heard Tim talk, and Steve Bart is our wild card person. Steve and I have ended up on various panels together, so these are all friends, I hope. But that doesn't mean we can't arm wrestle.
Mm-hmm. That's right.
So my first question is, I come into the sensor world from image sensors, which is a little bit separate. We're in many ways driving, in my mind, driving things. We have large arrays. Okay. And we have lots and lots of data, and we've got a big enough business to drive special processes. So if you take your iPhone apart, we've got a component in there which is made up of a pixel array as well as an ISP stacked on top of each other. We have a variety of non-standard metals or of materials being used because it's an optical transducer. And we've got 50 million pixels altogether, talking at ideally at somewhere between 30 and 120 frames per second with a good depth. So I'm curious as to what's happening in the rest of the sensor world and how they play together. So my first question to start this off is, where, if you think, each of you think about the sensors where is technology differentiating in your area? If we just want to pass that question along, we'll entertain questions from the audience as we go. We've got an hour.
Okay, should I start since I'm the wild card? I don't know. That's a big question, and I can think of several areas where I could speak about it. Mm-hmm. I came as part of TDK. I was part of the InvenSense company, for those of you who remember that, but their main product lines are IMUs, which means 3 axes of acceleration and 3 axes of gyro. And their other big product line is microphones. And they sell almost all of those into commercial markets, and particularly into very high volume markets like phones. Mm-hmm. And iRobot vacuum cleaners and Alexa and things like that. So the answer might be a little bit different for the IMU versus the microphone side. So when you were speaking, you were talking about arrays. Yeah. And in the area of inertial sensors, that's still, arrays of those devices are generally not necessary for the kinds of performance that those devices need. So what's driving the technology there is size and power. Particularly in phones, continuing to try to shrink, not so much the planar square area, but the thickness is the driver. The phone companies want them to be thinner and thinner and thinner. There's a constant desire to have bigger batteries and smaller electronics components. So a lot of that is about shrinkage and lower power. Yes. Because then the software that accompanies those sensors so that they aren't on all the time.
Yes. So something to think about is whether the lower power solutions for an IMU carry over to lower power in other sensors.
Right. And so, circuit technology breakthroughs can carry over. The physical changes in how they're built and how they're made thin can potentially carry over because those are, you know, you can only thin the silicon so much, but how you package it, you know, so a lot of the drivers today are trying to do packageless, you know, silicon, just bumping it right on the right on the circuit board. So that's the driver over on the inertial side. On the microphone side, there's always issues of size, but that's an area where arraying is starting to come to the fore, because the main figures of merit for microphones in these kinds of applications are the signal to noise ratio and the AOP, which is the acoustic overload level, okay? And so those things are sort of in contrast with each other, okay? If you want better signal to noise ratio, generally you make a less stiff microphone, and if you make a less stiff diaphragm, then the overload protection is worse. So in order to try to get both of those parameters to go up, you have to do something more. And so their arraying is starting to be, you know, something that's starting to drive.
On the microphones, are there phase, you know, directional?
Yeah, there are, sure. That's usually done at the system level. So you would buy 5 microphones and then the software piece of it would do the phasing. But yes, and there's some things you can do with the acoustics of the packaging to make that easier and better. But that's, honestly, that's more specialty. I don't want to say specialty, but you know, in a phone, that's not the big deal. In some aspects, it is. You know, this company Shure here, that's on the name of this microphone, makes a panel that they put on the ceiling in places that have 256 microphones in it, and that's all about phased arraying. Yeah. So anyway, those are some of the drivers that are happening in the area that I walk in.
Yeah, and the medical space is very broad, so I'll talk about the areas I know best. One of the things we've been doing is kind of slipstreaming behind the trends with Internet of Things. So our drivers are more kind of computation at the edge, because that would be, say, inside an implant or in a wearable, and then power and capability. So a lot of times the medical space isn't enough to drive the innovation, but we've had examples of great collaboration. So one, you know, decade plus ago was working on mainstream commercial suppliers of inertial units, and saying we have extreme power requirements that we need to have for an implant that you currently aren't meeting. Let's co-develop a system. We'll use it for an implant application. You can use it for anything else. And it ended up being, you know, a $1 billion+ application in the commercial space for doing micro power. And then we actually could use the same device to do brain implants, spinal cord stimulators, and the like. And so oftentimes I look for synergy in the commercial space, because the same idea of edge computation, lower power, better signal and noise, we have a shared interest in that space, but we don't necessarily drive the volumes. So we kind of look for partnerships there. And those are the trends that are continuing on right now.
Does wireless play a role in?
Yeah, so the wireless is critical. People may not be as familiar with this. Cardiac devices, I always say, are about 10 to 20 years ahead of the neuro right now. And part of it's just the volumes. So same thing in medical, volumes drive a lot of the innovation. So many of the medical devices, my uncle gave me permission to share his story. He's got an implantable cardiac monitor, and he'll get a phone call from his physician if he needs to be checked on the next morning. And so it kind of many devices every night. At midnight or so, they actually communicate with a little bedside monitor through their radio link. Many of them are Bluetooth now, encrypted Bluetooth, or the medical information communication band. And it downloads diagnostics from the implant, bedside, gets radioed to your doctor. There's an overarching algorithm that says, does this person need to be checked or not? And so that's becoming more and more a common practice. So kind of the check engine light, if you will, for patients. And that requires telemetry and a capable telemetry, same thing, low power, distance, encrypted plus, similar to what we see in the Internet of Things. You wake up, you do a burst of information, do it in a power efficient way.
And encryption's important too.
Encryption's very important, especially the regulators want it, patients want it. A little bit this is my personal opinion. People tend they say encryption in terms of reading out your physiological information, your brain waves and thoughts. That doesn't bother me as much. If you want to be bored to death with my thoughts, have at it. Actually, because I'd actually say Facebook algorithms, they've shown this, are also very capable at decoding you. And so it's already out there, my friends. And it's more, I worry more about encryption for stimulating and adjusting going in. So for me, I obsess much, much more about control of the functionality in the implant than data. But you got to do both from a regulatory perspective.
True.
Yeah, so I'll have a little bit different perspective to build on both these things. The one thing I'll talk about is actually the economics. So something, and Paul, please chime in based off your experience.
Stole mine. No.
I won't steal yours. I won't steal yours. Is when I showed the wafer starts on that one chart, it was going up at a very significant rate. Almost 9% is what we call about the compound annual growth. Something that changed, I think, about 20 years ago in the industry is they stopped shutting fabs down. It used to be very early on when you saw a technology shift, older fabs would close because they were no longer viable because there wasn't a technology need.
Yes.
So what was happening is you were having, okay, when I made that was a really awesome, nice chip from your birth year, I guess it was.
Yeah.
That fab would have been closed because it was running a very old technology. And those fabs are finding a new life because of Internet of Things, MEMS sensors. These kind of things are making it a lot more viable today. And actually the reason for that is it's much more cost effective because all the equipment in those fabs and those fabs themselves have been fully depreciated. So I know this is a technology conference, but when you're not paying the depreciation on all these expensive tools you bought, it's much more affordable to do this. For perspective, like the fabs that are running today with the most cutting edge, I think they cost about $8 billion.
Mm-hmm.
And some of that's the fab itself, the infrastructure, but a lot of that's the equipment. And then the finance people get a hold of that and depreciate it over 8 years. So that's why the chips have to be that expensive, is because not just the technology, but you're paying off all what you're doing. Once it's fully depreciated, you can get into very low entry point things like the medical, where you're looking for this. You need it to be cost effective. Mm-hmm. So this is really why you're seeing MEMS exploding and why you're finding more accessibility here because of that.
Yeah, I fully agree. And just to dovetail on that, the CMOS image sensors have benefited greatly from the semiconductor nodes that kind of precede them and drive the price down.
We're sort of 10 years behind.
Yeah, and MEMS and other sensing fabrication technologies, microfabrication, is more like 20 years behind, but still struggling to drive the cost down to make them viable for high volume mass production. InvenSense really pioneered ways to take advantage of that semiconductor technology. More sensor technologies need to envision the manufacturing piece of it. As you embark on flexible electronics and methodologies on this, it's imperative that you constantly be thinking about the economic aspects of it, because deployment of these technologies fully dependent on achieving price points that make them viable in the marketplace. And so often the most sophisticated sensors today are relegated to very small markets, and it becomes a defeating situation where you can never drive the cost out of it, because you're using 100 wafers a year. Even 1,000 wafers a year is nothing. You need things that will drive tens of thousands of wafers per year to kind of drive those economics, and really leverage the semiconductor technology. And this is one of the things that we're trying to wring out of a lot of the sensor early stage companies, is, are you able to meet the economics of the market to make this truly viable? So.
So that seems to be the case in my mind for the small companies, the ones you're worrying about.
Yeah.
How about for a TDK or an SC?
Yeah, I can jump in there. So economics for actually large volume products are in the consumer space are very difficult as well. And we do have the kinds of volumes that allow us to, have a reasonable scale in the fab. But there's another aspect to the economics, and that is commoditization. In other words, if you go out and you produce, an analog MEMS microphone, you can get, if you are lucky, you can get 17 cents for it. And so the difficulty is that, there's competitors in the market, and the people you're selling to are not hundreds of small companies. They're a very small handful of very powerful companies whose names we all know. And so the economics there drives people like us to try to get up the food chain, as it's described, by adding value. And that's generally, it can be these capabilities like power and things, but it's also largely software and system level behaviors. So it's digital functions and it's software. So just as an example, we sell a lot of inertial sensors into robot vacuum cleaners. And we do not output acceleration and rotational, gyro outputs. We don't do that. We actually write the software that decides whether the vacuum is on a rug or it just transferred to the floor, or whether it's come up to the step of the steps, or we write all that software. The vacuum cleaner company does not. And that's how we can obtain value. It's good for the vacuum cleaner company too, because they have a complicated system. They're very much happier if we're writing that software than they have to do it themselves. So, but back to the original question, just having a clever sensor is generally not enough. You really have to have the system pieces. You have to provide a solution, not a sensor. That's the buzzword now, is we don't make sensors. We make solutions for people's problems, and that's important.
Do you sell sensors or do you sell modules?
Well, our sensors have, because of the technology that we have, it's a bonded technology, so it's MEMS on CMOS. So everything we sell is an ASIC in and of itself. So if you look at it in that way, then even though it's in a package this big, it's kind of a module. Yeah. It's not a module. There are different ways to describe a module, but in the sense that there's processing power, not just signal conditioning. So therefore, it's a module in that sense.
I was wondering, because you talk about the software, whether you end up selling them a package, which is the component and the software and.
Yeah, I mean, we're selling this thing that has a sensor, it has processing, and it has an API, right? It has an interface, and they just talk to the API and say, did you turn left or right? How fast are you going? That kind of thing.
And that's the part that we're benefiting from on the medical space. So actually in my startup, we have an accelerometer, and we basically configure it to recognize different types of motion. It throws an interrupt. We then pull the interrupt and say, what type of motion, characteristic did you see? How do I map that to a stimulation algorithm? And it's all driven by these other consumer applications, but we can apply them as well.
So you're selling hardware and software.
Yeah, well, we use it, it's very much as the system perspective. We say we can provide this new therapy, so we tend to talk in the worlds of therapy as a solution for the clinicians, enabled by sensors, but driven by bootstrapping off of the commercial space. And you're asked just about an economics, so it's in the medical space, yes. There used to be captive semiconductor houses, and it's for the students, my interview questions, they always ask you at the end, do you have questions for us? So my standard interview questions are, what's your unique advantage over your competitors, and what is and same for your competitors' advantage over you, and what's your greatest weakness, and what are your competitor's greatest weakness. So the company I ended up with, their greatest competitive advantage is they had an internal fab that gave them advantages.
Oh.
The next day I interviewed at their competitors, and they said, Medtronic's greatest weakness is it has an internal fab. And so and actually the history books are actually a bit what Drew is saying, stopped making semiconductors, this is known, and redeployed the fab for things that were unique, because the internal captive, we just couldn't keep up with the TSMCs in the world, because once again, we really today with medical, I think the sweet spot is you slipstream behind what's Apple's driving and these others, and you take advantage of those innovations, and then anything you have internal, you're doing something very unique for your application, but something that really requires that internal innovation.
Yeah, so like in image sensors, we have some very unique processes to make a good photodiode. Is that something that you find that you need to find a fab that's willing to do something unique for you just to make the transducer work?
You have to have a really good reason, I think, to do that, because then it requires NRE. One of my projects in the past, they spent more time switching over the units and the testers to basically, they'd run on one tester a year's supply of our devices, and they spent more time running the golden units and getting basically to qualify the tester for that run.
Yes.
And so I think that's my spirit. I think for us, the innovation is what can I do to redeploy as much of commercial technology as possible? And that's would be my final point. We're, even in the National Health Service, it's the quality of life adjusted years, so the therapy benefit divided by the cost. And so anything that adds to the cost, you have to really justify, because otherwise you have to go to the clinical study and show you're providing disproportionate value, and that can be really hard. So I want to make the denominator as small as possible, and the way I do that is by trying as much as I can to leverage what Internet of Things is doing.
So just a little add-on to that, really to kind of say how that translates into what I see, is when you want to get into the lower cost, take advantage of slipstreaming in that structure, from a design standpoint, what it requires is thinking about, okay, how can I take advantage of components with existing design rules? So if you can take advantage of the IP library of a particular foundry or a design house, it becomes much more easy to get something into production in a cost-effective way, because they're already building on what they know. And then what I'm observing in the semi space is, of course, like we talked a little bit today about packaging, is you want to have your one component that's the most specialized, that's your secret sauce. But then everything in that 2D package system in package, if you can buy off the shelf, you're not having to go to the fab anymore. You're just going to a distribution house if you can take advantage of those things, either a cellular sensor, a Wi-Fi sensor, those kind of things. And having someone build that for you or being able to do it yourself, that's where you start seeing the advantage and the economies of scale.
I don't have a lot to add to that. I think we've hammered that pretty well. So yeah.
So sort of two questions. I'll decide which way to go here. One, the magic words these days. How is AI at the edge going to affect sensors? Is it going to happen? Is it not? Is it something that isn't required? The model in my mind is you have a sensor, you need something personalized in the way of processing, and then and it then efficiently sends it off to the cloud or to the main processor. Is that a good model, and will that become AI? Do we think that'll become AI? You want to go first?
I'll take a shot. I'll speak from the experience I've seen directly in the business I do, and within what I see in DuPont, is when it comes to AI, and even machine learning and then AI, you need to first think about how big the data set is. So when we think about how AI is used today, when they're slipstreaming off all this information we have from Facebook, there's a massive amount of data points that are voluntarily given to this data set.
Yes.
Now, when we're talking about sensors and those kind of things, the understanding has to be is, okay, how do I pool enough data inputs to actually have a valuable AI output? So finding that balance and finding out how you can get a large enough data set is going to be the biggest struggle before AI becomes viable. So when you send something off to the cloud, is that being uploaded to the cloud with enough other data that actually makes it valuable to do something predictive? I think maybe in medical that is a viable thing because you can normalize that data in a way that's useful. I don't know if it's going to be that way for every application.
Okay, want me to go next?
Go next.
All right, so I think the answer is yes and yes. But more specifically, so as I was saying before, there are areas where arrays are less necessary so far, and areas where arraying is becoming more and more important. And from the perspective where I sit, those areas where arraying is giving you performance, you now suddenly have tremendous amounts of data. You were speaking earlier about how much data is coming out of one of these photo detector arrays. So we, as we work on sort of the next platforms of things, we are very significantly adding machine learning capabilities because, frankly, they're necessary. Some of the things that we're doing, just sort of core physics-based models are it's not that they're too complicated, but they can't always handle the amount of data that's coming in. So building the machine learning models with the data set that you build the machine learning model with is still an effort. It still requires work. But I think more and more, when we see the evolution of ubiquitous sensors everywhere, I think it's going to continue to evolve and be necessary. Sensors, we have a vision of you walking into your kitchen area and there's a sensor on everything. And how does the refrigerator know you're talking to it and not the toaster, right? How does it know that? Well, you can say, well, it's got an array of microphones and it can tell you're looking at it. That's not really what you want. You want to be able to come in and say, hey, I'd love an ice cold glass of water, and the toaster knows that you're not talking to it. So that kind of stuff, machine learning in those contexts, I think is going to be the way people are going. We're working on technologies for gas sensing with multiple elements, and that is essentially a fingerprinting kind of requirement. And so there, machine learning is really the best mechanism for dealing with that data. And then finally, I'll add to this pile up here by saying, what I said before about not being commoditized and having more computation/intelligence, that's also driving the same sort of need to have machine learning based models that can give your sensor system value. So I think in 10 years it's going to be absolutely everywhere. Machine learning, not necessarily AI, but machine learning.
Yeah. So I'll give an example and then a caveat on the risk containment. So where we're doing some research in it now is on sleep staging and sleep therapies for people post-stroke. So this is just a specific example, but we have an algorithm that runs on a microprocessor using TinyML to optimize the algorithm, and that draws several hundred microwatts to run overnight. And so that's actually our primary power driver and limits the wearable lifetime. But we're leveraging the wake-up word chips. So I think it's sentient, makes this little, kind of neural network embodiment. And so it fits right into the target code. And we're prototyping with that now, and we drop down to a few microwatts. And so part of the reason that we're applying it is it's a very efficient way to do the algorithm itself. Now, the ML component of it is that when you have a stroke, your brain rhythms change. And so we actually have to do transfer learning on each patient. So we do one night of recording and basically come up with a customized solution for them that we can push out and get our accuracy up. And that pipeline becomes very efficient and scalable if we do it right. So I think as wake-up words and infrastructure that allows you to talk to your fridge or your toaster, we can actually apply that and use it for medical applications as well. Now, the reason I talked about risk is I think we do need to think about the downsides, and we go from the ML to the AI, so something that's going to actually respond and take action with patients. We need to create a safe bounding box for the actions that can be taken. And I think that's, if we think about it within some of these standards and some of the risk management protocols, I'll use the circle, clinicians can say that's the safe sandbox. And as long as you limit your actions within that sandbox, things will be okay. And then I found the regulators will allow you to try new algorithms and the like, because you can guarantee that there's a bounded space for these to operate. So I think it is going to happen. I think we'll benefit from all of the innovations of, computation at the edge, but with the caveat for each application, make sure you do risk assessments and limit what the AI can do.
So you don't want the AI in your pacemaker to start hallucinating? Is that?
Yeah, exactly. Or you talk to your pacemaker, but you meant to be talking to the toaster, but your pacemaker, when you say cook the subject, that's you don't want your defibrillator to kick off.
At Silicon Catalyst, we have 9 AI accelerator companies. 6 of them are very focused on very low power edge devices that work basically untethered. I think the key for creating very prolific sensing applications is that they don't have to go back to the cloud for this constant upstream and downstream of information so they can make decisions locally. That has to be done very inexpensively, but semiconductor technology can enable that. Some advancement in the model sizes and things like that, analog compute, all these things are starting to enable that. And I think we're at a very early stage. When you start talking about fields of deployment in agriculture and shop floor and things like that, you're talking thousands and thousands of sensors, and there's just no way to have a cloud connection. It has to be done locally, and but we see that coming actually faster than the sensor technology in some cases. So, yeah.
Yeah, one of the questions I have is if we have AI on the edge, can you train it separate from the cloud?
Yeah, there's been some work. One of my collaborators at Mayo Clinic, so Greg Worrell, and I think part of it's the time scale. So this is stuff people know about. So there's basically what's the time that you have to respond to. So in like an epilepsy device, you don't have the luxury of, say, telemetering up to the cloud, doing a complex computation and cutting bound, because you need to respond to this seizure onset within seconds or sub-seconds. So there's kind of local compute, but then what they do is distribute it. They'll do more longer-term averages, look for trends, run it, say, on a local processor, and then for the population level, they'll actually put it up into the cloud. And there's a company, NeuroPace, which is approved in the U.S. for responsive epilepsy. So they run the embedded algorithm in the device for the fast response. But their innovation is then they'll actually kind of phenotype the patients, put that up into the cloud. And so me as a community neurologist, I have my patient, I'm like, I have this real trouble with a non-responder. They'll actually upload the data to the NeuroPace data set. Their internal engineers and scientists will actually compare that patient's brain rhythms with their entire 5,000 plus database and push out a suggested prescription. And they've actually been able to show, using that kind of infrastructure of a distributed cloud for population level management, they're able to flip half of the non-responders into responders. And so that's right, say different types of computation at different scales. It'll be local and then also distributed.
I have one more thought on this subject, and that is that the other computation at the edge, which may mean AI at the edge, that's what we're talking about. There's a potential security aspect that's a good thing, and that is, if you think about, again, about ubiquitous sensors, maybe in your home, and there's a camera always on, always running, trying to, monitor you and see what you want and what you're doing. Well, you don't necessarily want those images of you walking around in your house in whatever state you're walking around in your house. You don't necessarily want those going up to the cloud. And so the ability for systems to be running at the edge and to be securitized so that those kinds of personal informations get computed, they give you results of interest, but they're not escaping, is something that it's something that hasn't really been addressed thoroughly yet, but it will definitely be important.
Okay. We have questions from the audience?
My question is kind of a shift in what we're talking about. Is that all right?
Yeah, that's fine.
I haven't yet today heard anything about photonics and photonic integrated circuits in particular, and the kinds of sensors that are enabled by that kind of thing, as well as what I've been realizing is kind of a tangential aspect as well. Any kind of sensors that can take advantage of quantum effects. In particular, the one that comes to mind is magnetometers that are going to be using color sensors. And I wondered if anyone on the panel had any thoughts on what is in the near future for existing and new uses of photonics for sensing purposes, as well as maybe the quantum aspect and how that leverages off of all the hype about quantum computing.
Yeah.
Yeah.
You had to mention earlier about LiDAR and the LiDAR bubble.
Yeah.
One of the questions I have right now is whether frequency modulated continuous wave units which are based on a photonic processor, are going to make LiDAR not be a player in the automotive.
Right. Actually, we just brought into our portfolio company out of Caltech that's basically bringing, a PIC technology that will basically outperform LiDAR at almost every level. So I think I do see that. I see metamaterials also having a huge impact here, co-integration of metamaterials with semiconductor processing, creating very high performance applications. They're mostly right now being applied to superscalar data centers and things like that, because there's a lot of money there, and everybody wants to try and come up with some solution to NVIDIA. But in the sensing world, there's a large number of applications there that it can be applied to. They just don't have the same economic urgency, I guess. But we've seen several things along that line. In the quantum space also, that potentially the next bubble of VC, partly because these quantum guys, they need a lot of money, like $500 million, $1 billion in development money, and they want astronomical valuations for this money, like $10 billion or $50 billion, and it's unjustifiable. But a lot of VCs are chasing it now because they see it as a building need. Hard to say, but I think it's already overheated a little bit, from my perspective.
Sure.
There was a talk earlier this week at the European version of this conference on room temperature quantum sensors and the possibility of them becoming computers. based on solid-state diamond. So.
I can make a quick comment from our perspective. We're kind of behind, and we're not doing very much in photonics per se, but maybe some old school. One of the areas that we are working in is photoacoustics, and so because we're very strong in acoustics, and we're trying to figure out the photo piece. So, our interest there is largely on light sources, quantum cascade lasers, or, new LED technologies that can be small enough and efficient enough to do those sensors. So we are doing that kind of stuff, but I haven't seen, I think maybe some of the stuff you're talking about, like actual, waveguide-based sensors and what is it I'm trying to think of, where you put lots of little stubs up there.
Like metasurface.
Metasurfaces, basically. Yeah, we're not doing much there.
So in the neurospace, the optically pumped magnetometers are actually relatively disruptive technology. And so the classic magnetometers required superconducting materials, so that I don't know if you've ever seen it. There's like, you put your head in, there's this massive vessel above you with the cryogenics. And so you were restricted to a lab. They cost a fortune, so there'd only be a few universities that had them, and you couldn't do anything. And then the other problem is because of the vessel and the cryogenics, the detectors themselves were actually spaced quite far from the surface of the brain. So now with these new optically pumped, it's room temperature, it's portable, and so it's enabling a lot of new neuroscience, and that's on the academic. But what people are doing is very excitedly starting to look at these for at-home diagnostics, because it's easier to do perhaps than an EEG. You can basically put this onto your head, you're getting a real-time readout, it's room temperature, taking room temperature quantum effects, and so that's a space I'd watch very carefully. It's really starting to take off within the clinical neuroscience space.
The self-diagnostic is a little scary, but it's
so
a home kit.
Yeah, so it's one of those, I mean, the pragmatic side of me is, until we can know what to do for early onset dementia and the like, it's kind of, I don't know, maybe ignorance is bliss, but in terms of these kind of at-home trackings and things to try to help people out, in the diagnostics, there is a space. So that's right. It's a disruptive from the standpoint, I don't know quite how it's going to emerge, but it's replacing the cryogenic chamber in the room with something you can use at home, and people are starting to apply it. I'm sure some interesting ideas are going to come out of the other side.
What about wireless sensing? For example, there's a lot of talk of something called integrated communication and sensing for 6G, and using the wireless network for doing probably position sensing, but there may be other kinds of sensing. And on a more local level or smaller level, there's a professor at MIT who's done a lot with position sensing of people using Wi-Fi. So has any of you run into any of this or heard about it or have anything to say?
No. We've been trying to keep our eye on the, what are they calling it? Smart cities. And a lot of that is distributed sensing throughout a city area. And of course, obviously, you need those communication networks in order to do that. I think that certainly is coming, a little bit on the slow side, because it's one of those things that has to catch on before companies say, oh, there's really a big enough market. So that we see, and it kind of falls somewhat into the area you're talking about, I think. But otherwise, not too much. I guess, and there are similar things going on with agriculture. Again, where a wide distributed network of sensors provides some particular value.
Yeah, the passive monitoring for a home it may be a different MIT startup or the same one you're thinking of, because I was just looking at their technology last week, but they're taking advantage of basically radio frequency waves to do monitoring as people move around. There's work at the dementia research in the UK on this, but basically kind of this passive monitoring. So you don't have, it's basically an array that's set up in the house, and all the privacy issues that you were mentioning are valid. But it does help, like a loved one takes a fall or starts to show erratic patterns. It can give you an early warning sign, and so that is being explored actively now for home use. And you can do more than just motion. They're now getting like breathing, some other elements coming off as well in terms of physiological monitors. So that passive behind-the-scenes monitoring, I think, is an opportunity, but at the same time, we have to avoid a dystopian future as well of being monitored when we don't want to be.
So are there other questions from the audience?
Great talk. Thank you for your time and insight. So we talked about AI and using them in your products. I'm interested, how are you using AI to improve your workflows or help you design better products or new MEMS technologies or make financial decisions and valuations?
I hear a lot of people asking that question. I hear very few people answering that question.
I saw it on your slide. 40% improvement using AI.
Yes.
Yeah,
So which is true. So it did help us with, kind of seeing some of that patterns and trends. I did try to share a couple examples, but maybe I'll expand a little bit on that. Especially in the chemistry space, being able to actually do that kind of molecular modeling like I was showing, or doing some of those DOEs that I showed from the cleaning space, those are things that actually are really nice, because then in terms of developing, one, you do it faster, but it's also very scalable once you do the front end work to build the data sets like I was talking about before, because then you can scale that very quickly across a variety of things. Like with the cleaning example I showed, which was the last slide, it went through 100,000 plus things, and then human went through and said, okay, this isn't viable because that particular version of the chemical isn't sourced at the volume we need, or maybe not at the price point. So, but it allowed you to kind of explore all those corners very early on. So that's at least how we're using it from the chemistry side. And now what we're trying to do is find more sophisticated ways to apply that to the process, not just on either a small molecule or doing a massive DOE with what can be openly sourced, but how do you make it more sophisticated? Because the formulations are incredibly complex, especially when you start looking at how that reacts with what the customer's process doing. That's a lot more variables. So it's how do we expand it to kind of cut down on the innovation cycle time so we actually can get faster to market.
Yeah, we see a lot of AI now being applied to chip design. The iterative approach to layout can be highly optimized by AI. And so the most Cadence and Synopsys are both investing a fair amount in that area. I think the outcome is going to be fantastic. When you're talking about GPUs and things like those massively large chips, the 50 billion transistors, the layout is an enormously difficult problem, and AI certainly can be of huge effect there. So.
Just maybe one more comment I'll put on. It's funny just to think about, because you're asking that question. There was a meeting earlier this week where someone was kind of scolding us that we need to get them the budget we need for our supercomputer use next year. So they're already kind of pushing, saying, hey, this one group already is allocated. You better tell us what you need or you could miss out. So it's being pushed at an enterprise level. There's certain groups that can really use it based off, they'd kill me for saying it, but the simplicity of kind of what they're doing versus others. But we're getting encouraged, they're actually getting the budget to make sure we find new applications for it. So we don't have to come up with the use case first and then justify the spend. It's more like, here's our allocation. First to give me a good idea is going to get to use this.
There's some real pragmatic application. I mean, it's more of customer facing, Like where we use it is when we're doing clinical studies, we have to write the patient information sheet and the informed consent. And so oftentimes those are asked, they'll say this needs to be understandable by an 8-year-old or someone with a 6th grade education. And what does that mean? And where we've written drafts of these documents, and then we'll actually put it into, say, ChatGPT or the like, and say, can you rewrite this for certain demographics? And oftentimes we'll write one master sheet in our speak, and then we'll create different versions. And it's not that we just output that and send it to the regulators, but we'll actually use that as a draft. And we find that that's very useful in terms of our workflow. And I think the quality of what we're providing is better from the standpoint of we're getting the right level set. I think that's when sometimes there's a sensor involved in our product, but we're using the AI actually in how we communicate the ideas and concepts for what we're trying to do.
So I think the time has come for each person to say whatever last thing they want to say, the pithy thing to have everybody remember.
Okay, well, the first thing I wanted to say is this is a great idea. I'm going to put my presentations to the CEO through this 8th grade process. I think that's going to help a lot.
Remember, this is recorded.
Oops. So I guess pithy is, clearly I think everyone here believes that the sensor universe around us is going to be increasing and increasing, and they're going to be more sophisticated and they're going to be more tied together. And the tricky bit for people who are trying to create new sensors is to find the ways that those sensors can collect value and not be simple commodities that just get sprinkled everywhere in the world, because that may be helpful. But it's not a great way to have a business, and so for all of those of us, and I include myself, who are fundamentally interested in physics and interested in sensor design, that's not enough. It's got to be a system, and it's got to solve the right problem for the right set of people.
So if we're looking for, you said pithy last comments. The way I'd frame it up is, we talked a lot about the cloud or AI, what we can do. I also shared kind of what we're doing here. But the one thing I do kind of guide and talk to people about, especially when it comes to doing machine learning and AI for sensors or other things, is it takes a lot of front-loaded work to build that data set, to build the algorithm, understand where you're getting. And when we talk to some of the newer scientists, some of the newer engineers around this, you can't discount a good linear regression some days. And so you really got to make sure that you have kind of ruled out that you can take some of the basic tools that we've been using for way too long before you go to some of these more sophisticated things, because of the time and energy it can actually use in the device. So you got to make sure you're using the right tool, so you don't, as I like to say, and I've heard from my dad, don't shoot a duck with a cannon.
Right. Yeah. If you don't know what a PCA is, don't do a machine learning algorithm. Right.
I guess my closing comment would be, there's a lot of young researchers and developers here. If I look back at the start of my career in 1981 and thought forward, I could never have imagined that we'd be here today with the kinds of advancements that we've had. I mean, when I got into the ASIC business, we were struggling to do 10,000 gates. So the very exciting thing about what you're doing today is that it's everything that you're working on today is part of an evolving technology that when you get to the end of your career, where most of us are, you will be amazed at that early work that you're working on right now, how it's affected the world, and keep that in mind, that this is the activity that is actually going to have a tremendous impact on at all levels of society. And so, I feel very fortunate to have been part of doing that and still contributing. So
just to reinforce, the sensor within a system is really critical. So it's, take a systems mindset. But for me, it's as my mom would always say, we hope for the best, so design for the best, but plan for the worst. And so I think, especially for the students, I find that designing for how the sensor-enabled system can go wrong and designing the mitigations for that is actually a lot of times more intellectually challenging and fun than actually just the baseline design. And I think once you understand those risks and design and the mitigations, the regulators and the customers will be much more likely to adopt your design.
I want to thank everybody for coming and staying, contributing.